Okay, so at the previous lecture we began to discuss compact operators between Banach spaces. So let's recall the definition. Suppose that X and Y are Banach spaces, and we say that a linear operator T from X to Y is compact if the image of the unit ball of X is relatively compact in Y, which means that the closure of this set is compact. The set of all compact operators from X to Y is denoted like this. K of xy, and if y equals x, then we write just k of x. At the previous lecture I stated a theorem about basic properties of compact operators, so I have no time to prove it, so let's now recall the statement and let's prove this result. First of all, I claim that the set of compact operators, K of xy, is a closed vector subspace. A closed vector subspace of the space of all bounded linear operators from X to Y. Second, if we have two linear operators, say T is a bounded operator from X to Y, and S is a bounded linear operator from Y to another Banach space Z, and if at least one of them is compact, so suppose that either S or T is compact, then so is the composition. The composition ST is also compact. And finally, if we have a bounded linear operator T from X to Y, then T is compact if and only if the dual operator T star, which acts from Y star to X star, is compact. So these are the basic properties of compact operators. The first two parts are due to Riss, who introduced compact operators in 1918. And the third part about duality is due to Schauder, and it was obtained around 1930. Okay, so let's now prove this result. Part one. So we take two compact operators, S and T, and we want to show that their sum is compact. So we take the sum of S and T and apply it to the unit ball of X. So clearly this set is contained in the sum of the images of the unit ball under S and under T. And by assumption, each of these two sets is relatively compact in Y. It's easy to see that the algebraic sum of two relatively compact sets is relatively compact. Well, indeed, the plus operation is continuous from Y cross Y to Y. And the continuous image of a compact set is compact. So this implies that a continuous image of a relatively compact set is relatively compact. And so this shows that S plus T is compact. S plus T is a compact operator. And similarly, we show that the product of a compact operator by a complex number is compact for each scalar lambda. So as usual, bold K denotes our base field, which is either the field of real numbers or the field of complex numbers. So this shows that compact operators, the set of compact operators is a vector subspace. Let's now show that this subspace is closed. So suppose that T sits in the closure of compact operators in the set of all bounded, in the space of all bounded operators from X to Y. And we want to show that T is compact. Well, it sits in the closure, so for each positive epsilon, we can find a compact operator S, from X to Y, such that the distance between S and T is less than epsilon. And since S is compact, it takes a unit ball to a relatively compact set, and relatively compact is equivalent to totally bounded. So since the image of the unit ball is totally bounded, we can find a finite epsilon net. Let F be a finite epsilon net for the image of the unit ball under S. Well, now this inequality, together with the triangle inequality, readily implies that the same set F is a 2 epsilon set for the image of the unit ball under T. F is a 2 epsilon net for T of B. This is just the triangle inequality. And since epsilon is arbitrary, we conclude that T is compact. So this set T of B is totally bounded. So the operator T is compact. Okay, so this proves the first part of our theorem. Let's now look at the second part. So suppose, for example, that S is compact. Let's look at the image of the unit ball under the composition S of T of B. Well, T is bounded. T is bounded, so it takes the unit ball to a bounded set. The set is bounded. And since S is compact, it takes each bounded set to a relatively compact set. And this means precisely that ST is compact. ST is compact. Okay, if we now assume that that T is compact, if T is compact, then again we look at the image of the unit ball, S of T of B1, and now T is compact. So we know that this set, T of B1, is relatively compact. Relatively compact. And S is bounded, or equivalently continuous. And a continuous map takes a relatively compact set to a relatively compact set. And again, this means precisely that ST is compact. And this completes the proof of the second part. Okay, and finally let's prove the third part of the theorem, which is due to Schauder. First of all, we prove the left to right implication, so we suppose that T is compact. Suppose that T is compact. Let's denote by K the closure of the image of the unit ball under T. So by assumption, this set is compact. And we want to show that the image of the unit ball in Y star is relatively compact or equivalently totally bounded. Totally bounded. As a preliminary step towards this goal, we take two functionals in this ball, say f and g, and let's try to calculate the distance between their images under T star. T star of f minus T star of g. Well, by the definition of the dual operator, this is equal to f composed with t minus g composed with t. And by the definition of the operator norm, this is equal to the supremum over the unit ball of x, f of t of x minus g of t of x. Or equivalently, when x runs over the unit ball, t of x runs over the image of the unit ball. So we can write this in the following way. The supremum over the image of the unit ball, f of y minus g of y. And if we now take here the closure of the unit of the set, the supremum will be the same for continuity reasons. So in other words, this is the supremum over k. So k is the closure of this set of f of y minus g of y. And this is nothing but the distance between f and g in the space C of k of continuous functions on k. Or more exactly, not between f and g, but between their restrictions to k. Okay. What can we deduce from this calculation? I claim that, let's denote this formula as 1. So formula, first of all, let's introduce some notation. We denote by m the set of all restrictions to k of all bounded functionals on the unit of all bounded functionals on Y star or on Y which belong to the unit ball. So M is a subset of C of k. And now this calculation, formula 1, implies that the following map that's denoted by phi from M to the image of the unit ball under T star. So phi takes the restriction of each such functional to k to T star of f. So phi is given by the following formula. Formula 1 implies that this map is well defined. And in fact is an isometric bijection. Between M and T star of B. Well, why is it so? First of all, why is it well defined? You have two linear functionals f and g such that their restrictions to k are the same. So this number is 0, and this chain of equalities implies that this number is also 0. So T star of f equals T star of g. And so this means that this map is well defined. And actually the same chain of equalities implies that this map is isometric. So the distances are the same. And just by the definition, by construction, it is surjective. It is surjective. So as a result, we see that it is an isometric bijection. And let's now recall that our goal was to show that this set, this space is totally bounded. But we now know that there is an isometric bijection between this set and M. So now, equivalently, we have now to show that M is totally bounded. So now to complete the proof, we have to show that M is totally bounded. Why is it more convenient than to show that this set is totally bounded? This is more convenient because M is contained in C of K. And we have a very useful criterion, namely the Arzelà-Ascoli theorem, which says that a subset in C of K is totally bounded if and only if it is bounded and equicontinuous. So that is, we have to show that M is bounded in C of K and equicontinuous. This is equivalent to the total boundedness by the Arzelà-Ascoli theorem. And this is very easy. Well, indeed. Let's denote the following constant. The supremum of norms of all elements in K. Since K is compact, this constant is of course finite. Then, for each bounded functional f in the unit ball of y star, and for each point x and k, the absolute value of f of x, of course, is less than or equal to the norm of x, because norm of f is less than or equal to 1. And the norm of x is less than or equal to c. And c is a constant. And so this implies that M is bounded. M is bounded in C of K. And to show that it is equicontinuous, we take 2 points in K, say x and y in K, and now the distance between their images, f of x and f of y, what is this? F is linear, so this is f of x minus y, and this can be estimated as the norm of x minus y, because the norm of f is less than or equal to 1. And this inequality readily implies that M is equicontinuous, because if this is smaller than epsilon, then this is also smaller than epsilon. So M is equicontinuous. And this completes the proof. So now we know that M is bounded and equicontinuous, so it is totally bounded by the Arzelà-Ascoli theorem. And since there is an isometric bijection between these two spaces, we conclude that the image of the unit ball under T star is totally bounded. So this completes the proof. Okay, an immediate corollary is that K of x, the space of compact operators on a Banach space, X, is a closed two-sided ideal of the algebra of all bounded operators on X. well, it's a closed subspace by property 1 of our theorem, and it is an ideal by condition 2. By the way, we will see at the end of our course that if X is a separable infinite-dimensional Hilbert space, then this is the only proper closed-two-sided ideal of B of X. And the same holds for some other nice Banach spaces, but not for all of them, of course. Okay, so this is corollary 1. Another corollary, before formulating the next corollary, let's introduce some notation.
And what about T star is compact and T?
Oh, sorry, I forgot to say about the opposite implication. But fortunately, this is very easy. Well, indeed. If we now assume that, well, maybe it's better to, I need a little bit more space here. So if we now assume that T star is compact, then by the first part of our proof, the bidual operator is compact. T double star is compact. And now we identify canonically X with the subspace of the bidual X double star and Y with the subspace of Y double star. And we know that in this case, T, after we make these identification, T becomes the restriction of T double star to X. And it's easily seen that a restriction of a compact operator onto any closed subspace is also compact. So this is a simple duality argument. Okay, thank you. So now the proof is complete. Okay, let's now introduce some notation. Again, if X and Y are Banach spaces, then we denote by script F of XY the space of all bounded finite rank operators. That is, those bounded operators from X to Y, such that the image of T is finite dimensional. And if Y equals X, then we write just F of X. So corollary 2, we already know that finite rank operators are compact. This is more or less immediate from the definition of a compact operator. But now we can say more. The closure of the set of all finite rank operators is contained in the set of compact operators, because this set is closed. And this is a very nice and useful sufficient condition for compactness. If we want to show that some operator is compact, sometimes it is more convenient to show that our operator can be approximated by finite rank operators, that it sits in the closure of f of xy. And at the end of the previous lecture, we have seen how this result works. Namely, we proved a compactness criterion for a diagonal operator on the little LP space. So if we have a bounded sequence, then we can define the respective diagonal operator on the little LP space. And we have shown that this operator is compact if and only if our original sequence vanishes at infinity. By the way, as for other examples of compact operators, many such examples are contained in the first exercise sheet, which is already on the web page of the course. So I recommend you to look at these examples. Probably one of the most important examples of compact operators is the Hilbert-Schmidt integral operator, which acts on the big L2 space. Okay, now let's consider the following special case, namely the case where the second space is a Hilbert space. It turns out that in this case, we have an equality. I have the following theorem. If X is a Banach space and H is a Hilbert space, then we have the following equality. In other words, each compact operator from X to H can be approximated by finite rank operators. Okay, so we take any compact operator. So let T be a compact operator from X to H, and let epsilon be a positive number. So since T is compact, we can find a finite epsilon net for the image of the unit ball. Let F in H be a finite epsilon net for the image of the unit ball. This is a finite set. Let now H0 denote the linear span of F. So this is finite dimensional subspace of H. In particular, it is closed in H. And we can write the following direct sum decomposition. H equals H0 plus the orthogonal complement. Now let P denote the orthogonal projection onto H0. The orthogonal projection onto H0. So that is P is a bounded operator on H, given by the following formula. It takes x0 plus x1 to x0 for each x0 in here and x1 in here. So clearly this is a linear operator on H. It is bounded, and moreover the Pythagorean theorem readily implies that the norm of P equals 1. Obviously, by the Pythagorean theorem, the norm of this sum is greater than or equal to the norm of x0, because the vectors are orthogonal to each other. And if x1 is 0, then this operator preserves the norm of x0, so its norm is 1. Of course, except for the trivial case where h0 is 0. But this is the degenerate case. In this case, there is nothing to prove. So now we want to show, so clearly P is a finite rank operator because H0 is finite dimensional. And we want to show that T is close to the composition of P and T. To see this, we do the following. We take any element X in the unit ball of X, and we find an element Y in our finite epsilon net F such that the distance between T of X and Y less than epsilon. And let's now try to calculate the distance between T of X and PT of X. Well, by the triangle inequality, this can be estimated as follows. This is less than or equal to Tx minus y plus y minus ptx. Equivalently, this can be written as follows. This is Tx minus y plus p applied to y minus tx. Simply because p of y equals y. Y sits in F, and p is the identity map on H0. So we have this. But now we know that the norm of p is 1. So the norm of the second summand is less than or equal to the norm of the first summand. And the norm of the first summand is less than epsilon. So we see that the sum is less than 2 epsilon. And this holds for each x in the unit ball of x. If we now take the supremum over the unit ball, we see that the distance between t and pt is less than or equal to 2 epsilon. But the image of p is finite dimensional, and so the image of pt is also finite dimensional. And we see that t can be approximated by finite rank operators. So this completes the proof. Well, initial question. Can we replace here H by an arbitrary Banach space? This question was first explicitly asked by Hildebrand in 1931, and later it was given the name of approximation problem. The first man who systematically studied the approximation problem was Grothendieck, and he introduced the following terminology. By definition, a Banach space X has the approximation property AP for short, if for each Banach space Y the following inequality holds. That is, each compact operator from y to x can be approximated by finite rank operators from y to x. So we have what we have just proved is that each Hilbert space has the approximation property. So Grothendieck introduced this definition. He systematically studied the approximation property. He gave many equivalent characterizations of this property. He found many relations between the approximation property and some other problems in functional analysis. And he proved that all classical Banach spaces have the approximation property. But even such a great man couldn't solve the approximation problem. So he didn't know if each Banach space has the approximation property. So the approximation problem was very hard. And it was hard for many reasons. One of the reasons was that this problem was related to another famous problem in functional analysis, namely the basis problem. So let me say a few words about the basis problem. First of all, we have the following definition. Suppose that X is a Banach space, and suppose we have a sequence En of elements of X. We say that En is a Schauder basis. Schauder basis. If each element X in our space can be uniquely decomposed, can be uniquely written as the following sum. Cn En for some numbers Cn. So this definition was introduced by Schroeder, and it is very natural. The reason is that many natural Banach spaces have Schroeder bases. By the way, before looking at examples, let's make a simple observation. Let's observe that, of course, this definition is meaningful only in the case where X is separable. If X has a Schroeder basis, then X is separable. Well, indeed, of course, if En is Schroeder basis, then the linear span of this sequence is dense in X. And we know that normed space is separable if and only if it has a dense vector subspace of countable dimension. Here's the simplest example of a Schroeder basis. Suppose X is the little LP space where P is finite, or the little C0 space. And let's denote by En the following element of X. So the identity is at the nth position and 0 is elsewhere. So it's almost immediate that En is a Schroeder basis. Another example, which is actually a special case of this one, an orthonormal basis of a separable Hilbert space. Is a Schroeder basis. But in fact, this is a special case of the previous example because each separable Hilbert space is unitarily isomorphic to the little L2 space in such a way that a fixed basis in our Hilbert space goes to this concrete basis En. In fact, many other classical spaces, classical Banach spaces, separable Banach spaces, have Schroeder bases. For example, if we take the big LP space, where P is bigger than 1, but less than infinity, on a closed interval of the real line, then the trigonometric system is a Schroeder basis. This result is due to Marcel Ries, a brother of Friedrich Ries, who introduced compact operators. This fails for the big L1 space due to some results of Lebesgue. But the big L1 space has another Schroeder basis, the so-called Haar system. If we take a space of continuous functions on the closed interval, C01, for example, then this space also has a Schroeder basis. The most concrete basis is the so-called Faber-Schroeder system, which consists of some specific piecewise linear functions. So all classical Banach spaces have Schroeder basis. So as a result, we have the following problem, which was explicitly stated by Banach in 1932. Does every separable Banach space have a basis? This theorem turned out to be very difficult, and it was closely related to the approximation problem because of the following fact, probably due to Grothendieck. If X has a basis, then X has the approximation property. The answer to the approximation problem, and at the same time to the basis problem, was given by Per, a Swedish-American mathematician, in 1973. He constructed an example of a separable Banach space without the approximation property. There is a separable Banach space without the approximation property. In particular, this space has no basis. The construction was quite involved. Of course, I cannot reproduce it here. Subsequently, there were some simplifications of his construction due to many mathematicians. But anyway, all known examples of such spaces are quite involved, so it's impossible to describe them in our introductory course. Okay, so we'll come back to compact operators later. And now we begin to study another important class of operators, namely Fredholm operators. So let's start with the definition of these operators. The definition is purely algebraic. Suppose we have two vector spaces, x and y. Just vector spaces, we don't assume that they are norm spaces. We say that a linear operator T from x to y is Fredholm in Russian we say Fredholmov operator if the kernel of T and the co-kernel of T are finite dimensional. Just in case, let me recall that the co-kernel of T is defined as the quotient of Y modulo the image of T. By the way, probably those of you who are familiar with the language of categories know that the notion of a co-kernel, as well as the notion of a kernel, can be defined in purely category theoretic terms, and they make sense for any category with zero object. So I must say that if we work in the category of Banach spaces or in the category of norm spaces, then the category theoretic co-kernel will be different from this co-kernel. So this is the pure algebraic co-kernel, or in other words, this is the co-kernel in the category of vector spaces. And the co-kernel of T in the category of norm spaces will be the quotient modulo the closure of the image. Nevertheless, when we speak about co-kernels, we will always understand co-kernels in this pure algebraic sense. I hope this will not lead to any confusion, because actually we will consider co-kernels only for those operators whose images are closed. So in this case, all the definitions of the co-kernel will be consistent. So this is our definition of a Fredholm operator. So it makes sense for any linear operator between vector spaces. But of course, we will be most interested in the case where x and y are Banach spaces. And in this case, we will always assume that T is bounded. If x and y are Banach spaces, then T is assumed to be bounded.
When we call it threshold.
Yeah, I'll explain this. So these operators, they are named after Ivar Fredholm, a Swedish mathematician who actually had no idea about linear operators and vector spaces. He worked at the end of the 19th century or at the beginning of the 20th century, and he worked in the integral equations. Subsequently, some of his results on integral equations were translated by Ries into the language of linear operators. But the modern definition of a Fredholm operator was given only in the 1940s by Dieudonné. So somehow these operators are motivated by results of Fredholm on integral equations. I'll tell you more about this later when we discuss the so-called Ries-Schauder theory of operators of the form 1 plus compact. Okay, let's look at some before looking at examples, we introduce the following important number related to any Fredholm operator. If T is a Fredholm operator from X to Y, then we define the index of T as follows. This is the dimension of the kernel minus the dimension of the co-kernel of T. We will see soon that this number has a number of nice and remarkable algebraic and topological properties. Actually, the class of Fredholm operators is very different from the class of compact operators. So morally, compact operators are small, while Fredholm operators are big in some sense. So they are very different. But we will see soon that there is a very nice relation between compact operators and Fredholm operators. So it is very convenient to study them simultaneously. But historically, this was not the case. Historically, compact operators were introduced much earlier than Fredholm operators. Okay, let's now look at some examples of Fredholm operators. First of all, a trivial example, example 1. If T is an isomorphism between X and Y, is a vector space isomorphism. Then of course T is Fredholm. Because the kernel and the co-kernel are trivial. And the index of T is 0. Example 2. So let P be a finite rank projection. Sorry, not a finite rank projection. Let P be a projection with a finite dimensional kernel. So, in other words, this means the following. This means that X can be decomposed as the direct sum of two vector subspaces x0 and x1, such that P acts by the following formula. For each x0 in the first summand and x1 in the second summand. And x0, which is the kernel of X, is finite dimensional. So x0 is the kernel, The kernel is finite dimensional, but because of this decomposition and because of this formula, it's easy to see that the image of P is x1. So the core kernel is isomorphic to x0. So the core kernel is also finite dimensional, and it has the same dimension as the kernel. So we conclude that P is Fredholm. P is Fredholm, and the index of P is 0. Example 3. Suppose now that both x and y are finite dimensional spaces. In this case, I claim that each linear operator T from x to y is Fredholm. This is obvious. And I claim that the index of T is the dimension of x minus the dimension of y. So in particular, it doesn't depend on the operator. It depends only on x and y. Well, indeed, if we calculate the index, so this is the dimension of the kernel minus the dimension of the core kernel. Let's write this explicitly. So this is the dimension of the kernel minus, and the dimension of the core kernel is, so the core kernel is y modulo the image. So this is the dimension of y minus the dimension of the image of T. Now let's write this in the following way. And it's a standard result of linear algebra that the sum, the dimension of the kernel plus the dimension of the image, equals the dimension of x. So we get this formula. In the special case where y equals x, we see that each linear operator from x to itself is a Fredholm operator of index 0. Of course, it's essential here that x is finite dimensional. In the infinite dimensional case, there are many Fredholm operators of non-zero index. And here's the simplest example. Example 4. Let x denote either the literal P space or the little C0 space. And let TL and TR denote the left shift operator and the right shift operator on X. Left shift and the right shift. Then it's easy to see that both of them are Fredholm. TL and TR are Fredholm. The index of the left shift equals 1, and the index of the right shift equals minus 1. Well, indeed, by the definition of the left shift, its kernel consists of all vectors such that the first coordinate is arbitrary and the other coordinates are 0. And clearly this space is one-dimensional. But the core kernel is trivial because the left shift is surjective. So the index of the left shift equals 1. If we now look at the right shift, first of all, it is injective, obviously, so the kernel is trivial. But the co-kernel is not trivial because it is not surjective. More exactly, the image of the right shift is a co-dimension 1 subspace, which consists of all vectors whose first coordinate is 0. So the co-dimension of the image is 1, that is, the dimension of the core kernel is 1, and so the index is -1. Some more examples of Fredholm operators will be given in the next exercise sheets, and more advanced examples of Fredholm operators will be discussed at the lectures. Let's now look at some properties of the index. So today, we will prove probably the most basic algebraic property of the index, namely the additivity of the index. So we have the following result. Theorem. Suppose that we have 3 vector spaces, x, y, and z, and 2 linear operators, t from x to y, and s from y to z, linear operators. Then we have the following results. First of all, if any 2 of the operators S, T, and ST are Fredholm, then so is the third one. In particular, the composition of 2 Fredholm operators is Fredholm. Property 2, if they are Fredholm, then we have the following formula. The index of ST equals the index of S plus the index of T. So the index is additive in this sense. And finally, statement 3, which is also sometimes useful. If we only know that ST is Fredholm, if ST is Fredholm, then the kernel of T and the co-kernel of S are finite dimensional. They are not necessarily Fredholm, but at least the kernel of T and the co-kernel of S are finite dimensional. A remarkable feature of this theorem is that this theorem has no canonical proof. There are several proofs of this result, and probably none of them is the best one. I will tell you the proof which I learned from Mikhail Vladimirovich Shubin, an outstanding mathematician who unfortunately died a few months ago. The proof is based on a couple of elementary lemmas. Lemma 1. Suppose that we have an exact sequence of the following form. So this is an exact sequence of finite dimensional vector spaces. then the following alternating sum of their dimensions is 0. The proof is an elementary exercise in linear algebra. Actually, this is more or less equivalent. This is more or less equivalent to this formula. This follows from this formula by induction. Lemma 2. Lemma 2 is a classic result. This is a special case of the so-called snake lemma. In Russian, Lemma zmiya. So suppose we have the following commutative diagram. Commutative diagram of the following form. x1, x2, x3. And we have 3 arrows here: alpha, beta, and gamma. So suppose this is a commutative diagram. Of vector spaces with exact rows. So both the rows are exact. In fact, it is not essential that we consider vector spaces. We can replace here vector spaces by modules over any ring, or even by objects of an arbitrary abelian category. I claim that in this case there exists an exact sequence of the following form. Well, so this is the snake lemma. The snake lemma. I will not prove this result because this is a classical fact from algebra, which is used very often in homological algebra, in algebraic topology, in commutative algebra, and in many algebraic fields of mathematics. Why is it called the snake lemma? Let's draw a picture. So let's imagine that the kernel of alpha sits here, the kernel of beta sits here, and the kernel of gamma sits here. And it's natural to draw the co-kernel of alpha here, the co-kernel of beta is here, and the co-kernel of gamma is here. So obviously, since the diagram is commutative, the restriction of this arrow to the kernel of alpha takes the kernel of alpha to the kernel of beta. So we have a natural arrow from here to here. So this is this arrow. And similarly, the kernel of beta goes to the kernel of gamma. Also, because this curve is commutative, it's easy to see that this arrow induces a well-defined map from the core kernel of alpha to the core kernel of beta. And similarly, this map induces a map from the core kernel of beta to the core kernel of gamma. The only map which is not obvious in this exact sequence is this one. And graphically, it can be written as the following snake from here to here. So this explains where the name of this lemma comes from. Okay, anyway, so this is the classic result. I'll not give you the proof. And let's now see how these two lemmas imply the additivity of the index. So proof of theorem. Let's consider the following diagram. So the first arrow looks as follows: x, x plus y, and y. And the arrows are defined as follows. So this notation means that this column consisting of the identity operator on x and the operator t takes each element little x from here to the pair little x and t of x, which sits in the direct sum. And this row minus t1 means that this operator takes each pair little x and little y to minus t of x plus y. So here 1 is the identity map of y. So the notation, I hope the notation is self-explanatory. So this is the first arrow, the first row of our diagram. The second row looks similarly. I have y, z plus y, and z. This arrow is the column s and 1, and this is the row minus 1 and s. And we also have three operators, three maps here, here, and here. This is s, this is t, and this is the direct sum of s, t, and the identity map of y. So this is our basic diagram. It's a straightforward exercise to show that the diagram commutes. Diagram commutes. And the rows are exact. So now we are in the setting of the snake lemma. So we apply the snake lemma, and we see that there is an exact sequence of the following form. Zero, then we have the kernel of S, the kernel of S, the kernel of ST plus 1, the kernel of T, the co-kernel of S, the co-kernel of ST plus 1, the co-kernel of T, and 0. Let's now observe that the kernel of ST plus 1 is obviously isomorphic to the kernel of ST, because the kernel of the identity map is trivial. And for the same reason, the co-kernel of ST plus 1 is isomorphic to the co-kernel of ST. Now, since the sequence is exact, this immediately gives us the first and the third parts of the theorem. Well, indeed, if, for example, S and T are Fredholm, and the sequence is exact, well, these two spaces are finite dimensional, And so this one is also finite dimensional. And these two are finite dimensional. So the middle space, this one is finite dimensional. And similarly, if, for example, S and ST are Fredholm, we conclude that T is Fredholm. So since everything follows from the obvious fact that if we have an exact sequence, then each member of the sequence which sits in between two finite dimensional spaces is also finite dimensional. And that's it. So this gives us part 1 and also part 3, because if ST is Fredholm, then this one is finite dimensional, and this is the kernel of S is a subspace of this one, so it is finite dimensional. And similarly, since the co-kernel of ST is finite dimensional, and since this sequence is exact, we conclude that the co-kernel of T is finite dimensional. As for the second part of the theorem, namely the additivity of the index, we apply Lemma 1. So this is a sequence of an exact sequence of finite dimensional vector spaces. So the alternating sum of their dimension is 0. So if we take this dimension with the plus sign, this one with the minus sign, plus, minus, plus, minus, and calculate the respective alternating sum, we get the following. These two members give us the index of S. These two spaces give us minus index of ST. And finally, these two give us the index of T. And the sum is 0. And this is equivalent to the additivity of the index. So the proof is complete. Well, probably the last result for today, if you don't mind, concerns a simple but useful property of Fredholm operators between Banach spaces. So now we again are in the setting of functional analysis. We have the following result, which is due to Kato, a Japanese mathematician. Suppose we have two Banach spaces, X and Y. And a bounded linear operator, T, from X to Y. And suppose that the image of T has finite codimension in Y. Or equivalently, well, equivalently this means that the co-kernel of T is finite dimensional. I claim that the image of T is closed in Y. In particular, this result implies that a Fredholm operator between Banach spaces has closed image. In particular, the image of a Fredholm operator is closed. This is very useful. Actually, long ago when Fredholm operators were just introduced, the closedness of the image was one of the axioms of a Fredholm operator. So the original definition was that a Fredholm operator is a bounded operator with a finite dimensional kernel, a finite dimensional co-kernel, and a closed image. But actually, the image will be closed automatically because of this result. The proof is a simple and nice application of the open mapping theorem. First of all, we may assume from the very beginning, that the kernel of T is trivial. Otherwise, if it is not trivial, we just quotient out the kernel and consider the induced operator from the quotient of x modulo the kernel to y. The image of this induced operator is the same as the image of t, and the kernel of this operator is trivial. So everything is easily reduced to the case where the kernel is trivial. Now, our assumption, by assumption, the kernel is finite dimensional. So there is a direct sum decomposition of y into direct sum of two spaces, the image of t and y0, where y0 is a finite dimensional subspace of y. Y0 is finite dimensional. We now consider the direct sum, so-called L infinity direct sum of x and y0, which is the algebraic direct sum equipped with norm, which is the maximum of the norms of the summons. So this norm on the direct sum is given by the following formula. So y0 is finite dimensional, so y0 is a Banach space, x is a Banach space. It's a simple exercise. We have already used this in our proof of the closed range theorem, that this is a Banach space. This is a Banach space, because both x and y0 are Banach spaces. Now consider the following operator, that's denoted by S, which acts from this direct sum of x plus y0 to y by the following formula. It takes each pair, little x and little y, to t of x plus y. So this direct sum goes to this direct sum. The kernel of t is trivial, so t is an isomorphism of x onto the image of t. And the identity map is an isomorphism of y0 onto itself. So this implies that S is a bijection. S is bijective and bounded. The boundedness of S is immediate from the boundedness of T. So S is bounded. Now Banach's open mapping theorem, or more precisely the inverse mapping theorem, implies that S is a topological isomorphism. To complete the proof, we observe that the image of T is nothing but S applied to x plus 0, just by the definition of S. And x plus 0 is easily seen to be closed in the L infinity direct sum. The subspace is closed in x plus y0. But we already know that S is a topological isomorphism, so it is a homomorphism of this sum onto Y. And each homomorphism takes closed sets to closed sets. So it is closed in Y. And this completes the proof. So we have shown that if the core kernel of T is finite dimensional, then the image is closed. Okay, so that's all for today. And at the next lecture, we obtain some duality results on linear operators and on Fredholm operators, and then begin to discuss the so-called Ritz-Schauder theorem, Ritz-Schauder theory, which gives us a useful relation between compact operators and Fredholm operators. Thank you.